Welcome, everyone. Today, we're diving into a fascinating challenge. How do social media giants like Twitter and Instagram generate your personalized timeline when user data is spread across dozens of separate databases, known as shards? It's a complex problem, but incredibly common in distributed systems. Our goal is to understand how to query these multiple shards simultaneously, merge the results in real time, and deliver a perfectly sorted feed to users in milliseconds. This requires a blend of clever parallel querying, intelligent merging strategies, and sophisticated caching. Let's get started and unravel this distributed mystery. So, how do we tackle the problem of slow, sequential queries across many shards? We use a pattern called fan-out query. Imagine broadcasting identical requests to all relevant database shards simultaneously, transforming a slow serial process into fast, parallel execution. The workflow involves sending requests to all shards, each shard processing its portion, and then a distributed merging process combines these partial results. Since each shard returns its data already sorted, we can then use K-way merge algorithms to efficiently combine these multiple sorted streams into one perfect, chronologically ordered timeline. This is key to handling millions of entries without breaking a sweat. This isn't just theory, it's how the biggest platforms operate. Take Twitter, for example. Their timeline generation involves coordinating across user graphs distributed across multiple data centers and numerous shards. When you refresh your feed, Twitter's service merges tweets from different shards based on your follow relationships, often across geographic regions. This builds upon foundational concepts like database sharding, which we might have covered previously, and specifically focuses on coordinating queries across those shards. Similarly, LinkedIn's feed generation queries dozens of database clusters, with the challenge scaling exponentially with user connections and content volume, showcasing the real-world demands for this architecture. Now, let's look at the key players in our cross-shard timeline service architecture. First, we have the timeline coordinator. This is the central orchestrator, managing all cross-shard queries and maintaining efficient connection pools to each database. Then, for each individual shard, we have a shard query manager. These managers handle specific shard connections, optimize queries, and even implement result caching to minimize latency. Finally, the merge engine is where the magic happens. It implements those distributed merge sort algorithms we discussed, combining all those partial timeline results into one coherent, chronologically ordered feed for the user. Understanding these components is crucial to building a robust system. Let's trace the journey of a timeline request through our system. The control flow begins when our timeline service receives a user's request. It then identifies which shards contain the user's social graph data, dispatches parallel queries to them, collects the partial results, and finally, the merge engine combines everything. This leads into the data flow patterns. Initially, parallel query distribution to all relevant shards, followed by our results aggregation phase where each shard returns its sorted data, and the merge engine assembles the final timeline. Throughout this process, state management tracks the query's lifecycle, moving through states like pending, dispatching, collecting, merging, and completed, ensuring we can monitor and handle any errors. This structured approach guarantees a smooth and efficient timeline generation.